NASA's new images of interstellar object 3I/Atlas weren't supposed to rewrite the rulebook, but when a quantum AI scoured the data, it flagged oddities even veteran astronomers hadn't noticed, like a sun-facing tail where standard physics says, "This should be impossible. This is only the third interstellar visitor ever spotted." Yet its behavior defies everything we thought we understood about comets. The results aren't just bizarre, they're deeply unsettling, with patterns no natural explanation can easily cover. If the world's most advanced AI is unsettled by what it found, shouldn't we be too? What is 3I/Atlas? And why has this discovery left even NASA's experts worried? The anomalies are just beginning. Dust streaming toward the sun from an interstellar comet is not supposed to happen. Yet that's exactly what the latest NASA images of 3I/Atlas reveal. A plume of particles stretching in the wrong direction, defying the basic rules of comet physics. Normally, sunlight pushes dust and gas away, forming a tail that points directly opposite the sun. That's radiation pressure in action, a force so predictable it's used to steer spacecraft. But here, the dust clings to the sunward side as if gravity and light are playing by a different set of rules. Spectroscopic scans add another layer to the puzzle. Astronomers look for telltale signs, specific fingerprints in the light spectrum that reveal what a comet is made of. In almost every active comet, you'll find clear markers, cyanogen, diatomic carbon, and other volatile gases glowing at precise wavelengths. These are the chemical signatures of a comet waking up as sunlight hits its icy core. But in the first weeks after discovery, 3I/Atlas showed none of these. No cyanogen, no diatomic carbon, not even faint traces. The spectrum was nearly blank, where it should have been lit up. Think of it like watching a campfire that burns hot, but produces no smoke. The dust was there, obvious, even dramatic in the images, but the usual chemical evidence was missing. It's as if the comet were venting material in a way no one expected, or from a composition that doesn't match anything seen in the solar system. Only months later, as the comet closed in on the sun, did a faint whiff of cyanogen finally appear. Late, weak, and still out of step with the dust activity. This combination, dust streaming sunward, a coma without its usual gas, and a delayed chemical response, has left researchers searching for answers. Some point to possible surface crusts hardened by billions of years in interstellar space, shielding inner ices from the sun's heat. Others wonder if the comet's spin axis is locked in just the right way to expose only certain regions. But the basic contradiction remains: a sun-facing tail, absent volatiles, and a profile that fits neither comet nor asteroid. For now, the EB physics just doesn't add up. NASA's imaging teams faced a challenge unlike any before. Calibrating the stacked exposures from the Atlas survey, they traced the faint moving point of 3I/Atlas frame by frame. Each pixel carried the weight of cosmic history. The resulting data pointed to a nucleus no smaller than 0.3 kilometers and possibly as large as 5.6 kilometers across. That's not just big for an interstellar visitor, it's enormous. For context, Oumuamua, the first known interstellar object, was likely less than 200 m long. 2I/Borisov measured about a kilometer. 3I/Atlas could be 5 times that or more. Only 3 confirmed interstellar objects have ever been recorded. To find one this large, this active, and this close is statistically staggering. The odds of randomly detecting such a giant, given the survey's sensitivity and the volume of space it covers, are vanishingly small. Most interstellar objects slip by unseen, lost in the glare of distant stars, or too faint for even the largest telescopes. Yet here the data chain is clear. From initial Atlas discovery to follow-up with Hubble and JWST, every image confirms the same immense active core. The object's brightness, measured across multiple nights and instruments, rules out small debris, or a swarm of fragments. This is a single monolithic body, an ancient traveler older than our sun, carrying material forged in a different star's disk. Astronomers tried to model how such a large interstellar object could cross our path. Simulations suggest the odds are less than 1 in a million for a random ejection from another system to land one so close to Earth's orbit. The scale alone raises questions about what else might be lurking in the dark, undetected. This is not just another comet. It's a statistical outlier, a cosmic heavyweight that defies the usual odds. The numbers demand attention, but the real shock comes from where it's going next. A trajectory that brings it alarmingly close to several major planets, one after another. Trajectory calculators at NASA and JPL started with a simple question. Where exactly is 3I/Atlas heading? The answer, it turns out, traces a path through the inner solar system that's anything but ordinary. On October 3rd, 2025, the comet will pass within 0.19 astronomical units, just 28 million kilometers of Mars. That's close enough for even the most conservative models to flag it as a near miss, especially for an object hurtling in from interstellar space. Only 4 weeks later, Atlas swings past the Sun at perihelion, reaching its maximum speed of 68 kilometers per s. Then, on November 3rd, it comes within 0.65 astronomical units of Venus. For context, that's inside the orbit of Earth, a region rarely crossed by any known comet, let alone one from outside the solar system. Each leg of this journey is mapped in fine detail, timestamps, distances, velocities, and the precise angles between the comet's track and the planetary orbits. The numbers are clear, but the pattern they form is anything but expected. It's a route that seems calculated, almost purposeful, as if the object is threading a cosmic needle between the inner planets. Gravitational assist basics explain how a planet's motion can accelerate or redirect a passing object. For 3I/Atlas, the effect is subtle but measurable. The comet's trajectory bends as it passes each planet, but the overall path remains hyperbolic, an open curve that will eventually fling it back into interstellar space. What stands out isn't the physics, but the sequence. Mars first, then Venus, each within a narrow window of time and space. Calculating these encounters requires precise knowledge of planetary positions, comet speed, and the Sun's gravitational pull, all of which have been confirmed by independent teams using NASA's Horizon system and JPL's DE 441 planetary ephemeris. The path through the inner solar system is now set. Each close approach is locked in by the laws of motion and gravity, but the odds of this specific sequence occurring by random chance remain an open question. What's certain is that the journey of 3I/Atlas is unlike anything astronomers have tracked before. The raw data points at 58 kilometers per s, October 2025, November 2025. Distances measured in tens of millions of kilometers paint a picture of a visitor following a route that defies easy explanation. And as the comet races toward its next planetary target, the stage is set for a deeper look at just how improbable this trajectory really is. Probability in astronomy is rarely this unforgiving. When Adam Hibbert and Abraham Lowe ran the numbers on 3I/Atlas's path, the results stunned even seasoned dynamicists. Monte Carlo simulations, essentially billions of random trials, were used to estimate how often an interstellar object entering the solar system with similar speed and inclination would pass as close to Mars, Venus, and Jupiter as 3I/Atlas is now set to do. This isn't just a matter of chance alignment. Each planet occupies a tiny slice of its orbit at any given time. For a hyperbolic visitor to pass within 0.119 astronomical units of Mars, then 0.65 astronomical units of Venus, and finally skim Jupiter's orbit, all within a few months, requires a sequence of timing and geometry that borders on the impossible. The simulations treated the entry time as a free variable, holding the object's velocity and trajectory fixed, and let the planets spin through their orbits. Most scenarios missed by tens or hundreds of millions of kilometers. Only a rare handful match the observed sequence. The analogy used by Lowe's group is striking. Imagine tossing a dart at a spinning globe and hitting 3 tiny cities in Shim-Sanmam succession, blindfolded, with the globe rotating between each throw. The odds don't just stack, they multiply, shrinking with every required planetary encounter. The raw output of the Monte Carlo study is a sea of near misses, with 3 I/Atlas say. Actual path standing out as a red dot in an otherwise empty patch of statistical space. Some researchers argue that with enough interstellar objects, even million-to-one events will eventually happen. But the sample size here is 3, and only 3 I/Atlas cuts this particular path. Quantum AI systems are built to spot what the human eye misses. When they processed the full stack of Atlas survey images for 3 I/Atlas, the first flag wasn't a shape or a color, it was a rhythm. The AI's period detection algorithms, running thousands of parallel checks, locked onto a repeating cycle in the comet's brightness. Not a random flicker, not the slow fade of a comet drifting from the sun, but a tight, persistent periodicity. Each pulse showed up right on schedule, like a heartbeat buried in the noise dot statistically comma. The signal passed every p-value threshold set by the researchers. The odds of this pattern appearing by chance in such a turbulent, dusty environment dropped below 1 in 10. Traditional analysis would have struggled here. Human astronomers might scan dozens of light curves in a night, looking for obvious dips or rises,